Well, greetings, mathletes, and welcome back. Um, so, in the previous lectures, we've looked at the graphs of sine and cosine and how we build those from the unit circle. Um, what we're going to be looking at now are the other four trig functions: tangent, cotangent, secant, and cosecant. And it turns out all of those are based on sine and cosine in one way or another. So we're going to take a look at those, and we're going to see how to build the graphs of the other four functions from the graphs of sine and cosine. So let's go ahead and take a look here, shall we? Okay, so if we understand the graphs of sine and cosine, the other four functions are just based on properties of fractions and the understanding we have of sine and cosine. So um, let's see here, we got brushes, turn that on, and let's say we have some function. Didn't I just do that? There we go. And the function, and I'm not even going to worry about what the expressions are in the function, just that there's a fraction involved, right? We have a numerator that and we have a denominator. And here's the properties I want to be thinking about when it comes to numerator and denominator. It has to do with when they're equal to zero. So if the numerator equals zero, that means the entire function equals zero. And if the whole function equals zero, that means wherever the numerator is zero, this is an x-intercept, right? Where the function's equal to zero, that's an x-intercept. Now, when the denominator is equal to zero, that's a problem because what that means is I have some kind of expression where I have a number divided by zero, right? If the denominator is zero. And that's an undefined quantity. And if I'm getting an undefined quantity, and we'll talk about a little bit more what this means, what you get is an asymptote. And I'm going to spell this out because it's not spelled the way it sounds. Right? Asymptote. So, what an asymptote is, and at least in this case, all of our asymptotes are going to be lines, but they don't always have to be lines. It's just some line that the function gets closer to, but never actually settles into that value. So there's different types of asymptotes. You could have asymptotes that do this and get closer and closer this way. You could have asymptotes that come in this way. They could be vertical, straight up and down. They could be sideways. It's just a line that the function approaches. In this case, where we have an undefined quantity, this is a vertical asymptote. Okay, so we're going to take a look at what that means. So let's go ahead and, oh yeah, we're over here, Control A, and let's go ahead and get rid of this. So remember what we just said, if the numerator is zero, the function has an x-intercept. If the denominator is zero, the function has an asymptote. So let's take a look at these. Let's start with, I'm just going to sketch a graph. Oh yeah. I'm going to sketch a graph of sine and cosine here. Right? And you should be able to sketch these at this point. You should know these 5 key points, right? And be able to sketch them. So that starts, remember it starts at 1 for sine, it goes down, crosses at pi over 2, bottoms out at pi negative 1, and then comes up to 3 pi over 2, 0, and then back up to 2 pi, right? It looks something like that. And then cosine, and I'm using x instead of theta because, well, they're pretty interchangeable in the long run, right? Oh my God, I just drew sine on cosine. Let me try this again. I can't believe I just did that. That's a rookie move. Okay, so let's try this one more time. This time, what am I doing? You know, they don't hand these degrees out to anybody. Or maybe they do, I don't know. Okay, so this one we want to be sine x this time. And let's see what I do, red. Yeah, sine x, same. Same 5 points. This time we start at 0, go up, right? And it bottoms out at 3 pi over 2 and then back up to 2 pi. Right? Boy, I still can't believe I just drew the wrong thing on there. That's pretty bad. Okay. Now, these graphs are just here as a map. They're a quick visual reference for us so we understand what the values of sine and cosine are at different points. Notice by looking at this, cosine is equal to 0 at pi over 2 and at 3 pi over 2. Sine is equal to 0 at 0, pi, and 2 pi. So what I want to do is use this knowledge to take a look at tangent. So let's take a look at some function g of x is equal to tangent x. Okay, now tangent's one thing, but we have a quotient identity that says we can identify tangent as sine over cosine. Right? Well, we can use the zeros of these to actually get a hold of some of this stuff. So I'm going to go ahead and draw a graph. And let's see here. Let's do this. So we'll go 2 pi. And I'm just starting out this way. This is a good way to start out graphing your functions. Just go ahead. It's made of two functions that are periodic and they have the same period. So the ratio is likely to have the same period or fit into the same period somehow. Now, that may not be the case, but it's fairly likely, so you might as well check it out. And let's do some negative values too. In fact, typically, when you look at the full graph of tangent, we'll see this in a minute, it's pretty typical to look at negative values also. So let's go ahead and take a look here. Let's look at our main points. Right, so this is going to be x and tangent x. Okay, so normally we look at 0. Let's see what happens at 0. So at 0, it's sine over cosine. At 0, sine is 0. And remember, sine is the numerator. So wherever the numerator is 0, we have zeros. So that means I have a 0 at 0. We know also that sine is 0 at pi, so that means at pi I get 0, and sine is also 0 at 2 pi. So that means that we have zeros here, here, and here. We can actually go in the negative direction. You notice they're equally spaced as you go across. Each one of them has a distance of pi between those zeros. Okay, so these are for zeros. Now, if I want asymptotes, I look at cosine. So I'm going to run out of room if I keep doing this. Yeah. So cosine is 0 at pi over 2 and at 3 pi over 2. So these are all vertical asymptotes. In fact, with all the trig functions, the asymptotes are going to be vertical. But wherever the denominator is 0, we get an asymptote. So it actually turns out it's 0 here at negative pi over 2 as well. And then over here at 3 pi over 2. Now, this is kind of interesting. To figure out where this goes, this is one of those things where, let me take a look here. One of the places we look at to get a hold of tangent is at pi over 4 and negative pi over 4. Okay, now at pi over 4, tangent's equal to 1, and at negative pi over 4, it's equal to negative 1. the way this ends up working, if you look at pi over 4 is 45 degrees, right? If I look at sine of pi over 4 over cosine of pi over 4, well, that ends up being root 2 over 2 divided by root 2 over 2, which is 1, because it's something divided by itself. So that's why tangent ends up being 1 here. That ends up being kind of an anchor point for you to be able to manipulate the amplitude. Okay, so it actually turns out that once you have these things marked, and really what you really need are the zeros, the asymptotes, and where you're equal to 1, the tangent curve does this, right? It has this weird little shape. And really, you have to kind of play with the numbers to see the whole thing, but it ends up repeating over here and over here and over here. And so it just keeps doing the same thing over and over and over again. It looks like a chorus line of dancers, all with their arms up in the air. Woo! Yeah, believe it or not, I'm not a dancer. Okay, so let me clean this up a little bit so we can kind of get an idea of what this looks like. Right? The main thing you want to get out of this is what one period of tangent looks like and where the asymptotes are. So tangent, completely unshifted, without changing the period, without changing the amplitude, without doing any phase shifts, tangent runs from negative pi over 2 to pi over 2 for one period, right? You can just get rid of the rest of this stuff because most of the time we're just interested in one period, right? And we can say some things. Okay, so you get asymptotes. Well, if you remember, I wish I hadn't erased it now, but I needed the room. We had asymptotes at pi over 2, 3 pi over 2. It actually went on to 5 pi over 2, and we had negative pi over 2. Right? You notice all of these are exactly pi apart, right? And they're all multiples of pi over 2. Now, there's a couple of ways to do this. What your book says is these are odd multiples of pi over 2, right? Which is fine. They're odd multiples. This is 3 times pi over, this is 1 times pi over 2. This is 3 times pi over 2. This is 5 times pi over 2. So 1, 3, 5. They are the odd ones. Another way to write this would be that, oh, that's what's going on there. What do you call it? I like to start it with negative pi over 2. So it's the multiples of pi, n times pi, minus pi over 2. Right? So if you start at pi, right, and subtract pi over 2, you end up with pi over 2. If I start with 2 pi and I subtract pi over 2, I get 3 pi over 2. So this is actually a little more formulaic. Your book just says odd multiples of pi over 2. We will need the other formula later on as we work through things. But for now, it's fine to just say odd multiples of pi over 2. Now, after seeing that, we should actually be able to kind of cobble together cotangent. Because it's really just a matter of getting a hold of the main pieces. So let's see if we can do that with cotangent. Notice it's still going to be based on the graphs of sine and cosine. Right? Remember, cotangent is cosine over sine. Let's do this. So let's see if we can piece this one together. So cosine x over sine x. Again, I'm going to center this one more because we saw from tangent that it was kind of more central. I'm going to mark some of my main stuff here. This time I'm going to go from, let's do pi, pi over 2, negative pi over 2, and negative pi. And then we'll throw a 3 pi over 2 in here, see what happens. Okay, so zeros come from the numerator, right? So we need to figure out where cosine is 0. So we look over here, cosine is 0 at pi over 2, right? Because I can see that, and at 3 pi over 2. And if we continue on, back on this side, negative pi over 2, right? So these are all zeros here. And then the other one would be negative 3 pi over 2. That's enough for what we have right now. Okay, so those are our zeros. Now, remember the denominator will give us asymptotes. And if we look at where sine is 0, we have an asymptote on the y-axis, because that's 0. And then we have one at pi. And then I have one at 2 pi, which would be out here somewhere. Now on the negative side, I would have one at negative pi. And so, you may have a guess that maybe it does something like this, right? But it turns out it doesn't. If we go ahead and look at the values again, right? If I look at this pi over 4, if I plugged pi over 4 into cosine and sine, it's the same values I got before. They're both root 2 over 2 divided by root 2 over 2. And so the value here at pi over 4 is equal to 1, right? If I went ahead and computed it here, it would be equal to negative 1. And so what ends up happening as I do this is cotangent actually goes the opposite direction. It's shifted over and flipped around from cosine, or from tangent, excuse me. Now you have to know how these things are graphed. And instead of memorizing them, it's a lot easier to build these things off of sine and cosine. So you remember all your anchor points depending on the zeros of sine and the zeros of cosine. So remember, for all of these things, and we're going to be using these same graphs for all 4 of these functions, if the numerator is 0, then the function has an x-intercept there. If the denominator is 0, then the function has an asymptote there, right? And we've seen this pretty clearly here with these first 2. Okay, so let's go ahead and clear. I don't want to clear the whole thing. Let's just get this off of here, and we'll look at secant and cosecant and see how those 2 things pan out together. And it turns out that those are all based on the graphs of sine and cosine as well. And as a matter of fact, with secant and cosecant, it's very convenient to have the graph of sine and cosine there first, and then you graph secant and cosecant on top of it. Okay, so we want to remember that if I'm looking at secant, right, f of x equals secant x. Secant, well, actually, I'm not going to use an arrow, it's an equals. Secant is 1 over cosine x, right? And so let's notice some things about this. So 1, the numerator can never be equal to 0. So that means there's no x-intercepts. It never crosses the x-axis. The denominator, though, can be 0. So wherever cosine is 0, we have asymptotes. So if we're going to go ahead and graph this thing, let's go ahead and take a look. Let's start with a graph of cosine, and we'll see how nice this is. So let's see here. We got 2 pi over 2, and 3 pi over 2. Now let's see if I can pull off graphing the cosine instead of graphing sine. So it goes from 1 to negative 1. So let's see here. So cosine at 0 is 1. And we want to take this, in fact, I'm going to move this around a little bit. This is going to go down this way and then over to here, up to here, and finishing a full circuit, and it continues from there, right? But this gives us the stuff we need. So looking at this, I have a 0 everywhere it crosses everywhere cosine crosses the x-axis is a 1 over 0 for secant. So that means I have an asymptote here through pi over 2, and I also have an asymptote here through 3 pi over 2. Now, the rest of this is really straightforward because, cosine is 1 here. Well, what's the reciprocal of 1? It's 1. So that means secant has a value of 1 right there also. And if this was continually going downward, it would cross the x-axis. It can't. So what it actually ends up doing is going up this way. Over here, it's at -1 here at the peak where cosine is equal to -1, and then it goes this way. And then back over here again, we have the same business. And so you can use the actual graph of cosine to figure out what secant looks like, right? It's just the reciprocal things. It's basically like if you took these guys and bent them downward, they would join up and become cosine, right? Same thing here. This would have to bend the other way. But, yeah. So as soon as you have your anchor points, one of the other things you might want to think about is the fact that, secant, and it actually turns out it's true with cosecant, can never enter this area between 1 and -1. Secant itself, right, if I take cosine out of this, and remember what we're graphing is secant, not cosine. This is actually what the secant curve looks like. You have these, oops. It's basically a bunch of u's flipped upside down and right side up and alternating, right? And it actually turns out that cosecant looks about the same. So let's go ahead and do this. Okay. Now, so here's what I want you to do. So we did secant last time. This time I want to look at f of x equals cosecant. And remember, cosecant is 1 over sine. So let's see here. So you should go ahead and graph your little, make a little graph, same kind of thing. 2 pi, pi over 2, and 3 pi over 2. So what I want you to do is see if you can go ahead and graph a sine curve and see if you can use the sine curve to come up with the graph of cosecant. So just spend a few minutes and see what you can deduce. The worst thing that can happen is you're wrong, right? And then you get it corrected when you watch the rest of the video. So give it a stab. It's a good way to tell whether you're actually understanding this or not. I'm just going to watch you work. Okay, so let's go ahead and take a look here. Now, the sine curve, if we'll go from -1 to 1, and starts here, goes up, hits pi over 2, hits pi, -1 at 3 pi over 2, and back up to 0 at 2 pi. Right? So we need to dice out where our asymptotes are going to be. And looking at this, anywhere sine is 0 is going to be an asymptote. So that means here at 0, I have an asymptote. Right? At pi, I have an asymptote. And at 2 pi, I have an asymptote. Okay, well, from here, the ones of sine are ones of cosecant because the reciprocal of 1 is 1. And I can't go down because I'll have an x-intercept, and I know I don't have any on this. So this actually cosecant ends up doing this and has asymptotes every pi radians. If we want to see what the actual graph of cosecant is, we erase the sine because sine's not actually part of it. Sine is just what we use to graph it, just like cosine. So if I erase this, that's more or less what the graph of cosecant looks like. And you know, you'd have another one over here, and the same thing here. It alternates as you go, right? Okay, so those are fairly straightforward. It's a matter of mapping out the zeros, that gives you your asymptotes, and also figuring out where your ones are. And basically, the peaks of sine become the troughs, right? These points of cosecant. And the same thing with cosine. So cosine and secant, sine and cosecant, those guys are the ones that go together. And that reciprocal identity is actually really important. Okay, so we've been through the basic graphs now. So I just want to talk about how some of this other stuff plays out. And I'm more going to focus on secant and cosecant as far as this goes. And then in the next lecture, we'll start focusing a little more on tangent and cotangent. So we're actually going to split this section up into 2 lectures, I think, just because there's a whole lot in this section. Okay, so yeah, let's go ahead and clear this off. And okay, so let's suppose we have been tasked with graphing. I don't like that color. Let's do black. There we go. We want to graph f of x is equal to 3 secant x. Right? That's what we're looking at. So here's how you think about it. What we want is this is the same thing as well, we'll write it this way. 3 times 1 over cosine x, right? Now, the way this ends up playing out, what we do is we graph here's our, how do I want to call it? Our secret graph that we're going to use is 3 cosine x, right? We're going to start with that. Now, it gets a little bit messed up because of the 1 over cosine, but once we have 3 cosine x graphed, we can graph secant x the same way we graphed secant before off of the cosine, right? Zeros become asymptotes and peaks and troughs become the peaks and troughs of secant. So let's take a look here. So let's start with 3 times cosine x. And let's see if I can actually graph a cosine curve this time. Well, clearly I can. It's the sine curve apparently I can't do. So let's see. The 3 would change my amplitude to 3. So that means I roam between 3 and -3. And then cosine starts here. Well, let's get these guys in here. Let's see. We've got 2 pi over 2, 3 pi over 2, and let's see, cosine does this. Right, it comes down through here. All right. So this is what 3 times cosine x looks like. So 3 times secant, we can build off of this thing. And I'm going to build it in purple. So zeros become asymptotes. So I have an asymptote here, and peaks and troughs become peaks and troughs. So there's a peak, and that becomes a trough, right? This thing's going to do this. Well, it'll do it, except it'll be a smooth line. There we go. And the same thing down here. Same thing up here. Right? So it should look something like this. And then the final graph, honestly, your homework does ask you to graph sine and cosine and then, graph your secant or what have you. But I do want to emphasize, because I've had this happen many times in the past where students get the impression that the graph of sine or cosine have to be part of it. They're not part of the graph. The actual graph looks like this, right? It's without the sine or the cosine curve. This is just scaffolding. It's like when you're working on a building and they have those things on the outside. Once the building's finished, you take it down so you can see the building. This is the building, right? Everything else was just to help build it. So this is how we find secant. So basically, whatever's being done up here, up here, if you've changed the amplitude, if you've changed the period, if there's a phase shift, you do the same thing to either sine or cosine appropriately. And then you just graph off of the sine and cosine curve. So if you know how to graph sine and cosine completely, you can always graph secant and cosecant, right? That's what it always ends up boiling down to. So let's look at another one here. Okay, so let's say I have g of x is equal to cosecant x over 2. Okay, so our secret graph that we're looking at, remember cosecant and sine are the two that go together, right? We know that cosecant, this would be the same thing as 1 over sine of x over 2, right? Because that's the definition of cosecant. It's the reciprocal of sine. Notice the x over 2 came down. Well, what does that x over 2 do to sine? Well, what it does is it changes the period. So remember, when you're looking at sine bx, the period is equal to 2 pi over b. Well, in this case, right, if I have x over 2, this is 1/2 times x. So b is 1/2. So 2 pi over 1/2, well, if I multiply by the reciprocal, is 4 pi. So my period is 4 pi. So when I graph this cosecant, I know my period has changed to 4 pi. So that means I'm coming out here to 4 pi. That means half of that is 2 pi. And then the quarters are pi and 3 pi over... No, just 3 pi. I was going to say over 2 because that was, that's the habit. All right. So now we have cosecant here. I don't have any amplitude change for sine, so that means we're still running from -1 to 1. And let's see what sine of x over 2 looks like. Sine starts at 0, peaks out at pi, down. Let's see, that's going to come back up this way. Something along those lines. Right? So as soon as we have that, we don't even, once you understand it, you don't really have to do a lot of reasoning. You just look for zeros. Here's my zeros. And then I just need to mark my peaks and troughs. This is a horrible drawing, but we get the idea, hopefully. Right? So your actual graph looks like this. And like I said, your homework does say put both the sine curve and the cosecant curve on the same graph. And that's fine, but I do want you to just understand that even though you're doing that, the sine curve is not part of the graph. I know I'm repeating myself a lot, but I just don't want it to be missed. That's one of those things that throws students off later on down the road. So, okay. Now, so let's go ahead and take a look at another example here. This time we're going to kind of throw stuff together. So let's say that f of x is equal to -2 secant 3x. Okay, so we're secant. That means that we're dealing with cosine, right? Because secant's the reciprocal of cosine. Now, so our secret graph, the one that we want to graph first so that we can figure out what secant looks like. Boy, I just realized those words are close. Secret and secant. Yeah, secant is more biblical. I think it was the Beatitudes that said, "Secant you shall find." Yeah, you didn't know there was a bunch of trigonometry in the Bible. Okay, now let's see here. So the secret one that I'm going to be graphing is -2 cosine 3x, and that's the one we're going to be using to figure out what secant looks like. So let's go ahead and graph this one. So we have an amplitude and it's negative. So that means we're flipped, right? That's a vertical flip. And we run from 2 to -2. Wow. Okay, and now we have to figure out our period. So remember our period is 2 pi over b. So that's 2 pi over 3. And that's it. 2 pi over 3 is actually where this thing starts to repeat itself. Notice it's just 1/3 of the previous period, right? I just divided it by 3, so it's 1/3 the size. If I want half of that, it would be pi over 3. If you really need to figure out what, once you have the period, right? I'm going to do this. Once I have the period, how do I want to do it? I'm going to make it not formulaic. Whatever the period, yes, I am going to make it formulaic. Once you have the period, basically what you do to find your new points, it's 0 times the period, pi over 2 times the period, or excuse me, 1/2 times the period. Let's try this one more time. 1/4 times the period, 1/2 times the period, 3/4 times the period, and then 1 times the period. And so what we just worked out was 1 times the period, which is 2 pi over 3, and then 1/2 the period, which is pi over 3, and then 1/4 of the period would be pi over 6, and 3/4 of the period, well, let's see here. That should be, is that half? Let's just double check because that feels a little bit weird. So it'd be 3/4 times 2 pi over 3. So the 3's cancel. Yeah, I get 1/2. Okay. So this is at pi over 2. Okay. Now, I'm going to bring these down a little bit just so I have a little more vertical room. We'll do it here. So we'll just shrink the scale a little bit. We'll call that 2 and -2. Okay. Now, we need to sketch in our cosine now. And it's negative, so that means instead of starting up here at 2, we start at -2 and we run the whole thing backwards. So it should do this, right? And then once you have that, you should be able to put in your secant. Once you have that cosine graphed, it's just, once again, a matter of putting in the asymptotes where you have zeros and then drawing stuff off of peaks and troughs. Something like that. And again, the only part that's actually the graph of -2 secant 3x is the part that's in purple, right? So it's this part here and here. That's a little bit better. Yeah, because scribbling is nice. I learned that in kindergarten. Okay, so again, let me try this. Let's try this again here. The main point here is that you can deduce the graphs of everything else from the graphs of sine and cosine. So pretty much all of these, you're going to start with a graph of sine and cosine, and then from there, you're just going to graph off of the peaks and troughs. When it comes to tangent and cotangent, it's very similar. You're looking for asymptotes where the denominator is 0 and zeros where the numerator is 0, and then you can start piecing it together from there. We're going to look at look at these graphs one more time. We're going to make them a little bit more complicated in the next lecture. And pretty much all we're going to be looking at are examples this next time. I'm not really going to be talking about new concepts, but how to apply old concepts in new ways. So in any case, we're done for now. And so until next time, keep your pencils and your wits sharp.